Welcome everyone to Mark Voids a Warranty. It's been a week, man, of not tearing stuff apart, and it's made me kind of sad. But the good news is we get to take stuff apart. But before I get started and show you what we're doing today, I want to show you what lies ahead if you can get me more subscribers. Oh, how do I do this here? Jeez. So, I was at a scrapyard, and I'm not faking. This thing is heavy. I got a TV production camera lens. This is the type of stuff they use on studio cameras in TV studios. They don't take these out into the field too often because the lens elements are the size of my head. These things are huge. It even attracted our cat, Fat Ollie, to look. Anyways, once we get to a measly 500 subscribers, let me put this down here real quick. Once we get to 500, I'm going to set up some cameras outside and take that apart. It won't fit on my desk here. So we'll have to figure that out. But let me show you just how close we are. We need camera 7. See this little curve down here? That's us taking off. So we're already on a very good upward trend ever since we started trying to gain subscribers. I'd like to continue that. And then one other thing while we have this over here, I recently won the Keysight Smart Bitch Challenge. Keysight chose not to publish my video. I can't figure out why for the life of me. I was hoping if I showed you guys just a small portion of it, maybe you'll see some things that you might know why they didn't publish it. But if not, that's cool too. So let's see if we have audio here.
Hi, I'm Mark, and I am the original winner of Keysight's Benchtop Contest. That's right, these 4 beautiful tools right behind me are really going to help me with some of my experiments. I mean, we do all sorts of stuff here, but I found that it's really, really important to keep a clean and orderly desk surface, and nothing on here doesn't serve a purpose. Nothing. So, before I get started telling you a little bit about my experiments, let me show you around these new tools. We'll just get rid of some of those things there. So, right here, we've got the benchtop power supply. Down on the bottom, because it's heavy. And sitting on top, we've got Keysight's, looks like the digital storage oscilloscope. That's going to be great. Right over here near the crackers, we've got a 5.5-digit multimeter, and just above it, a waveform generator with, count them, 1, 2 channels, right? Those aren't the channels. Those are the channels. So it's going to be a lot of fun. But before we get to using the tools, let me show you a little bit about the type of stuff that I do here.
Anyhow, that's the first half. I don't know, maybe it's the lighting, but if you see anything wrong with that and you want to let me know in the comments, I would love to know. You can view that probably just by Googling Keysight Smart Bench Essentials. Thank you, or checking out our LinkedIn, our Facebook. We have links to it there. So with that, let's go ahead and transfer over to what we are doing today. Today, I have for you something that's pretty cool. We need this shot right here. We've got a little bit of Keyence. So right here, we've got a communication platform, right, RJ45, and it's supposed to connect to a PLC, programmable logic controller. And this one's just an interface that interfaces to these little guys. And these are all optical amplifiers. These things all have lasers. Sharks with lasers. These all have lasers coming out of them. Well, LEDs. And you're supposed to plug fiber optic cable into each one of these and then run it to whatever you're going to run it to, and then have the return signal come into the sensor right there. Now, the way that these things are supposed to work, it's just, I have these up because it's easier to get rid of the glare. But the way that these things are supposed to work, you set a limit for when this, when you've got enough of the light returned to you. All I'm doing here is just putting my finger and letting the light bounce off of it. And when it exceeds the limit, it's on, and when it doesn't exceed the limit, it's off. So you could use this to create object detectors on an assembly line. If you've got a can or something, let's see if I can zoom out a little for you. That's not the right button. So there we go. So if you've got something in front of, again, you wouldn't run it directly off this. You would run some fiber optic cable. I just don't have any to run. But if you had something in front of the sensor, you could send that signal to a PLC. The PLC would realize it, and then, off you go. Unfortunately, I don't have anything to interface to this. I don't really have anything to do with this. But I'm going to see if I can't save this and only destroy one of these in the process of taking things apart. And we'll go from there. So let's get started. The first thing I'm going to do is kill the power. So before I do that, let me show you a little bit more about these. They're really, really tiny, and I'm sure they're well built. I mean, it's Keyence stuff. But these LCDs, or not LCDs, but LED arrays, these 7-segment LEDs are incredibly tiny. I don't even know how you source those. These things are maybe a 1/4 inch tall, maybe. It's not very much at all, whatever it is. They've got green over here, red over here, another red LED here, some tiny switches, preset, mode, LD, I don't know what that is, up and down buttons, I'm sure I can figure those out, and then set point. So this is probably where you, oh, it's locked, okay, locked, yay, set. So here's where you can set at what point you're going to decide these things are on, and at what point you're going to decide these things are off. So anyhow, that's probably all we're going to see with power, if that's cool with you. If you have any questions as we go through here, I do have a chat window open, and I do look at it from time to time. I'd be happy to comment or answer questions if I can. So we've just got a DIN rail mount and a clamp that's keeping everything pushed together. So all I did was remove the clamp. I've turned off the power. I'm going to get that in the network out of the way. Try not to hurt myself there. Put those down so we don't break them off. And then finally, I'm just going to pull that little power pigtail I made out. Hopefully. Come on, big guy. There we go. And we'll turn off our power supply. All right. So there we are. I think we could probably do with a slightly, keep hitting that wrong button. Could probably do with a slightly wider view. So I am just going to see, oh, they just slide right apart. Easy peasy. And that leaves a gaping hole there that, and I bet you this is a cover. Yep. Okay. So we've extracted one successfully. That didn't take long at all. And then I'll just lightly tighten this stuff back down. And then over on the other side, we've got the same issue. I think I need a slightly larger screwdriver there. All right. So these are our two items of interest. The instrument amplifier itself, which is the one with the LEDs, and this is, where's our model number? There we go. It's a Keyence FS-N10 optical instrument amplifier. And these daisy chain through a female receptacle on one side and a male receptacle on the bottom, or on the other. That's tiny, tiny. We're going to have to pull out the microscope to look at those a little better. There's a protective cover that's been molded to protect the switches from accidentally moving. That's kind of cool. I mean, it's a neat little piece of kit. We'll have to figure out how that opens up. And then we've got the communications interface, again by Keyence, and I guess this is NU-EP1 Ethernet IP interface. All right, so let's get started with this one. Looks like we've got 2 screws that have to come out. And I probably need to go to my smaller screwdriver. All right, I'm interested to see what makes Keyence Keyence. They've got good stuff, good reputations. This stuff is used in factories all over the world. Never heard anybody complain about Keyence on anything other than the price. I mean, you pay for it. But they've got quite an ecosystem of products. Precision machine cameras. I think we took one of those apart last week. They've got all sorts of things for factories. So I got while I'm looking for how to get some screwdrivers and take this stuff apart, and probably give you guys a wider view. I got this stuff at auction. A factory was downsizing. This was a battery factory, if I remember correctly. And the people that took this apart were absolute knuckle-dragging mouth breathers. They just went through with a pair of knives and just sliced through all of the wire harnesses, all of them. For the digital cameras, the Keyence cameras, the the control modules like I have here, they just didn't care. Didn't even bother unplugging stuff, which would have actually been easier. They just cut through all the cables. Now, some of those cable assemblies are hundreds and hundreds of dollars by themselves, and it's single source. You got to get them from Keyence. So, I mean, that was just unnecessary in my opinion. But what are you going to do? Okay, so this is our first look of inside the communications interface. So we've got 2 boards connected by some long headers, a reset button hiding here, some edge mount LEDs, RJ45 jack. This is kind of an interesting board connection setup. And we're held in place by the power jack. So something there is catching. I don't know that it's actually attached, but it's certainly in the way. So it's gotta go. I am live. Where's my hammer? Must not have been an Energizer factory. Yeah. Christian, that's a great question. Where is the hammer of Thor? It's got to be around here somewhere. I'm going to have to find it. I like playing Mark Smash. I really like playing Mark Smash. Well, thanks for joining us today, buddy. I hope you and Tracy and Ricky and the gang and Tess and Victor and Bob and everybody's doing well over there. I'll be visiting the factory around the 27th or 28th. Maybe we can grab lunch or something. All right, so here is our two boards. And I might have to do a tiny bit of soldering to properly get those apart, but that might be a good opportunity to show you guys how to desolder. All right, so some of the things that we see immediately is they do have ground pores and ground pores with a big separation. And they did a via fill. You know, these are easy patterns to implement. The reason that you do that is to usually prevent the copper pores from becoming unintentional radiators, right? These things can become antennas if you're not careful. So they have these tied to other plane layers. It's something I like doing on designs too. Usually the reason that you have these things separated are for high voltages, you know, creepage and clearance. The interesting thing though is that I mean, I don't know why you would need high voltage, you know, why you would worry about creepage and clearance on a board. Oh, maybe it's PoE. Maybe it's got power over Ethernet. But even then, that's a big clearance. We've got what looks like a programming header or debug header over here on the edge. So let's fire up the... we'll fire up the old soldering iron and start taking a look at this. Now, as far as taking things apart goes, I'm going to want to repeat this distance when I put it back together. So if I can move these headers to that side. Nope, I can't. So it's probably safest to take off this bottom board to separate that. And then I can use the headers as the spacing for reassembly. That way it'll fit back into the container that it is. I don't know. Christian, I cannot make a promise not to break anything. I like breaking things. It's one of the few joys that I have in life. Especially, and it's not my stuff, buddy. I mean... But thank you. I do appreciate you joining me today. All right. So the way that you typically go about desoldering, right, if you just heat up solder, it will liquefy. But once you remove the thing, it's still going to be stuck there. So you could sit there and you can work it, or you can use this stuff called desoldering braid. But before I do any of that, the first thing I'm going to do is make my tip nice and shiny. Heat doesn't flow well through schmutz. It flows very well through metals. So if you have a nice shiny conductor, you're good to go. All right, so this is braided copper infused with a little bit of flux. So when you heat the soldering wick near the solder joint, the flux melts. It helps the solder to flow, and then it gets sucked into the wire braid, so you can remove solder. Isn't that clever? It would probably be easier for everybody to see if I moved over to our microscope cam. Boom, boom, boom. Let's see here. Do I have a microscope cam set up? I don't. So we will do it the old-fashioned way. I'm going to have to disappear for a minute. I hope you don't mind. All right, so this is our edge. And all that we're going to do whoops. Is press that down and let the solder soak up into the braid as much as possible. And then I'm going to move to the next piece. And the next piece. And the next one. So what we're looking for is to get, and I'm going to have to get a little bit, cut that off and put a little new on, but we're just trying to get those holes open. So I'm going to flip to the other side, pull some more solder out, and then we'll cut off the edge of the solder wick and we'll suck out even more. So solder wick is a real easy way to take things apart and fix things. And if you do anything with electronics, you need to learn how to fix stuff, because it's never ever the easy way. I think in my life I've had one project go as planned. Come on. So Christian, how are things going over at the shop, buddy? Anything new in life? Okay. We seem to have lost Christian. Or there's a huge delay on the line. That could be the case too. What's going on here? Oh, I soldered it. Haha, whoops. My bad. I soldered my wick to the board. I'm not able to melt. There's needs more heat than I'm able to deliver here. Might have to up my temperature some. So the issue that I'm having right now, I don't know if you guys can see it, but you know, I'm not melting the solder. And I was melting the solder before. So I'm going to bump up my temperature about 20 degrees here, well, 25. And the plan is to be able to dump more heat into that board. And I'm going to bring this all a little closer to me. Make my life a little bit easier. Oh, except I kind of hurt you guys there. Super busy Friday. You guys have super busy every day, Christian. This is actually interesting, and it's probably a problem I caused, but see that little ring of schmutz between the pin and the solder? That could create potentially a cold solder joint, and it's probably because I'm screwing around with this stuff. Tell you what I'm going to do. I'm going to cut the end off and get myself some clean braid, and we're going to try this stuff again. I don't know why it's hating on me right now. It's making me look bad in front of my friends. Oh, Christian's saving up for his flight to space. I'll tell you what you do, Christian. Start getting a hold of the board files and engraving your name onto each one. So every time the SpaceX engineers get a board back, they see your name. And eventually what you do is you go down to SpaceX, you put on a nice suit, and you show up. And tell them you're there for astronaut training. And they'd be all, who are you? And then you say, let's go take a look at the spaceship. And then you show them your name on every single board. It's a very simple plan. You can do it, buddy. You can do it. You're going to get in space. The trick, though, is to carry a clipboard and wear a hard hat, so you look important. So what's going to happen to your commute when you have to go to Huntington Beach each day when you relocate? I tell you, buddy, I will work on improving the latency of these. Was also talking to Mahir about potentially getting a video editor for these so they're not so long. Wouldn't that be cool? Okay, we're making progress. It is not fast progress, but we are making progress. I don't know if this braid's a little old or not. It really does seem to be a heat problem. So it could be that we've got heavy copper here, and that's what's throwing me off. It's certainly a possibility. Investing in the chopper soon. What chopper's that, buddy? You know, you say you like watching the work, man. I wish I was giving a better example right now. I almost think I didn't increase the temperature enough, but I don't like having it this high. We'll see. It's up another 10 degrees. So the thing that I'm complaining about is that I can't get enough heat into the copper braid in these to melt them at the same time. So the heat could be traveling down here, but I didn't have that trouble on the other pins. So the other option is there could be some heavy copper inside this board that is just wicking the heat away. It's just transferring. Copper's got an incredible conductivity. The only metal that's better is silver. But the issue that you have, if you increase the temperature and you're around stuff too long, you can really damage things. You can cause the board to delaminate. You can damage components. There's all sorts of bad things that can happen. But the good news is I am starting to get this this stuff clear. But see, it's taken a really long time to melt. So that heat is just getting sucked away somewhere. So the plan is to suck away a lot of this stuff, and then I am going to clean up the end of my wick, and then I'm going to go back through and try to suck out a little bit more. So I'm going to let that side of the board cool down, and I'm going to see if I can't clear out these holes a little bit. This is pretty standard rework stuff. There's a couple other techniques that you can use too. You know, you can heat these things up and then apply a vacuum suction to suck the solder out. I've only ever had cheap tools. I've never had a proper one that does that, so I never really liked that. But if you have a good vacuum system, that should theoretically work really, really well. But see how we're just clearing those holes right out? Getting all that solder out. Oh, isn't that good? Okay, so we've got, it looks like 4 clean holes on that side. Now, this side should have cooled a little, so I'm just going to come through and see if I can't get the rest of the solder out of those. And you can see that icky flux all over the place, can't you? Come on, big guy. You don't want solder in that hole anymore, do you? Another method that I could use would be a heat gun. It's just kind of noisy. Wish I could get this stuff a little flatter, but this copper braid is really hot to the touch, and I'm not wearing gloves. Maybe gloves would help. Come on. Well, we still have Christian on the line. So Christian, Do you and Tracy commute to work together every day, or do you guys go in separate? This is really taking much longer than it should. This is where it gets close to being hammer time. It's not even liquefying in like 10 seconds. That's nuts. That is nuts. Give me one moment here. We've got an angry kitty. Oh, nope, Chester, I'm not following you. I've trained my cat to basically train me to go get fresh water every time he wants it. He's a lazy boy. All right, let's get back to an overhead view and we'll finish this up. There we go. All right, so the plan then is that these things have very little amounts of solder that are left in them. Which means if you apply a tiny bit of heat, and maybe this would be a good job for the heat gun, you should be able to separate these without much work. So I am just gently applying some force to separate these boards, or try to anyway. Let's see, there is something I could do. I'm hesitant to do it, but I think I've kept you all waiting long enough. I can replace these. That other side's going to take me like 15 more minutes, and I would hate to keep you waiting through that. But anyways, that's the procedure. You would heat it up and you would pull it out. Now that I've separated them, I do have to remove those pins. The way that you do that, I'm only going to do a few of them for demo purposes, but the way that you do that is to heat and push or heat and pull. So the plan is to yes, Christian, there's a cat in the back there. His name's Chester, and he's a lazy boy. He's getting old and opinionated. Every time he's thirsty, he demands fresh water, and I have to go fill up the cat bowl with fresh water so he can have that. I know, right? He's spoiled. So anyhow, the plan here is we're just going to heat these things up, and when they're hot, apply a little bit of pressure. Start pushing them through. Because we're going to have this stuff clear. I'm using a really small pick, which makes it kind of challenging. I should have gotten a bigger one. What are you going to do? So I got a call, Christian, from Huntington earlier, the new shop down there, and we're going to be doing some videos in the very near future. Have you had a chance to visit yet? If not, maybe I can take you as a cameraman. That could be kind of fun. Hang out for a little while, grab lunch. Okay, so what I'm doing here is just trying to clear those holes and prep them for resolder. So all I did was heat each of those pins, and then while they were hot, I just shoved them right through. And if you pull off the plastic bit, it goes a little easier. But, you know, we've one more heat up and poke with the thing, and we would have that. All right, so I'm not going to trouble you by showing you the rest of that. We can see the boards now. That's what we wanted to do. I am going to heat up this little piece of copper shielding and see if I can't remove that so we can see what's underneath. I am really getting a little bit suspect here about what's going on. I'm just retinning my tip. I usually don't have this much trouble desoldering things. So it's making me wonder if the temperature that I have set isn't actually the temperature that these boards are at. I did retin the tip a moment ago. That does help with heat flow. But look how long it's taking to melt these blobs of solder. Unless they used some exotic solder that has a much higher melting temperature than I believe it to have, I shouldn't be having this much trouble. Come on. Okay. So that's just a little heat shield, and that reveals the board. We've got a little piece of plastic. I can pop that off as well. And then we can start looking at this. That one's just glued on. Oh, whoops. That's no big deal. I've got copper in the garage. Come on, big guy. Yep, it is. There are some big things coming. I don't know what, but I just got a call from them this morning about 8:30, and they asked me to come down and do some videos for them. So I'm excited. I'm pretty sure I'm going next week on the 27th or 28th when Greg and LD and Shane show up. So we'll see. Okay, we have our first complete view of the board. And there are some interesting things. Like, for example, we've got this trace down here towards the edges that runs, and it doesn't appear to be covered in LPI solder mask. That's kind of weird. You know what we need to do is transition over to the microscope. You guys ready? Let's take a look at this thing. This should give you a oh, wrong camera. I'm sorry. There we go. All right. So a couple things that I thought are interesting, and I really don't know why, unless it might have been a mistake. But they have this trace down here with no LPI solder mask. They also have schmutz on their board. This is flux that's left over from through-hole soldering. Usually you don't want to leave flux on because it, you know, if it's an acid, flux is an acid, and it can sit there and eat your joints over time. So you want to, if you can, always wash your boards. Even if you use no clean flux, just because you have no clean flux doesn't mean you have a no clean board. There's lots of contaminants introduced in the manufacturing process, and you want to get rid of those whenever you can. All right, so a couple of things I noticed. It looks like on all of their land pads, they're using thermal reliefs. You noticed how much trouble I had desoldering things. Well, you can have the same amount of trouble. Come here, buddy. Come here, my sad kitty. Oh, there you go. Anyways, You noticed how much trouble I had desoldering things. Well, you can have the same amount of trouble soldering them if the heat dumps into the copper instead of the joint. So you use thermal reliefs to limit the heat flow. So that's why you see these things connected to these big copper pores by tiny little slivers. Most of their vias seem to be of a consistent size. They all appear to be through hole, but every now and again you see one like what got interrupted here on D1 something 0. They changed via sizes for some reason that escapes me. Look at all that contamination. Yuck. Mike Conrad would be sad if he saw this board. One of the things that's important, but you don't often see engineers do, you see this sliver here? That can become a radiating element. That can become a little mini antenna. So it's really nice that they tied it at both ends with vias. And these might be micro vias based on the size and the appearance. They might not. They could just be tinted. I'd have to increase the magnification to know for sure. But interesting stuff. There's a piece of something over this. Might be a polyimide coating over this chip. I don't see any manufacturer's markings that I immediately recognize. But overall, it's a pretty clean layout. They've, got their traces. I don't think those are differential pairs. They just happen to, well, they might be. Yeah, these are differentials that are running into the mag jack, the RJ45 jack. Another thing that you often see around magnetics is copper voiding. There's no copper here. It's just fiberglass. So these are connected to the data pins. I'm guessing these two big fat ones are for PoE, power over Ethernet. And then those immediately go from the mag jack to the other board, right? These are the holes we cleared out a minute ago. They still need a little cleanup. But I mean, overall, a reasonably clean design. Everything's laid out. Look how close they put that crystal. That thing is tight. You want to do that. It lowers radiated emissions. And the closer you can get it, the better. I've never seen one that flipping close. That's beautiful. You just want to make sure when you do something like that, that you aren't violating courtyards. If you get it too close, your assembly shop is going to get mad at you. And they actually might have here. There might be a reason I've never seen stuff this close. Usually, this is sufficient, right? You've got what looks to be a large array of decoupling capacitors, all with vias tying them down. But look how close these things are. The issue that you have here is if there's something wrong, there's just no room to rework. IPC defines 3 material classes for courtyard specifications. It's 3 material classes for land patterns. Least, nominal, and most, or minimum, nominal, maximum. I forget exactly how they're doing it. But basically they're saying how much extra copper you're going to put underneath each pin so that you can get these fillets to form. Where's my pointer here? Right? How much bigger is the copper on the board going to be than the part so that you get these fillets to form? And along with that, you get courtyards. Space around each part. See, you can kind of roughly see the shape here with this silk screen that you want to keep out of so that if there's a problem, if you need to rework, whatever, then there's room to do it. But man, what would I do here? I would have to hit everything with a heat gun and grab tweezers and hope I do it right. It'd be difficult. So anyways, that's the one side. Let's take a look at the other. These are dense boards, friends. So they did a good job of, you know, every time you see a sliver, they tied, well, not every time. You can see they tied it here, but then they didn't on, oh no, they did. So I guess that one's the via there. Okay, I lied. I was wrong. ST Micro. Oh, sorry, it's upside down. STM 32F103. I don't know enough about STM to know about that chip in any detail. Looks like we've got, there must be a copper internal layer, because these are the vias that I believe to be decoupling caps. Here we've got a right angle switch, an inductor. So this must be part of the power rectification. I really don't understand why they did these bigger vias. I'm sure they had an excellent reason. I just don't know what it is. And here it looks like we've got serial resistors. Interesting. Are they voltage dividers? It must be. So really the only reason to use two resistors is because of the drop in potential difference across each one. So, you know, for example, R28, you've got a resistor, and then you've got another resistor here, and you tap it in the middle. Well, the tap in the middle, you know, if these resistors have the same value, the tap in the middle is going to be half the voltage. So it looks like this is just a bank of voltage dividers for some reason. There's a lot of them. Wonder if the other side tells us anything. No. I really don't know what's going on there. Sorry, TV viewers. Interesting, interesting. So one of the things you always want to be careful of with vias is that the, you know, registration errors, which these all appear to be, or drill wanders, can cause these via holes to pop out. So whenever you can, you want to make your annular rings around your vias a little bit bigger than the manufacturing minimums, if you have space to do it. And you always want to teardrop or neck down or keyhole your vias in case that misregistration or the drill wander is in the direction of your trace. You don't want it to drill out and break the trace and then not plate it. And another thing I typically do whenever possible is use multiple vias to tie connections from plane to plane. But I also don't like putting vias in the middle of a Y branch, because that's 3 opportunities for drill wander error to break your net. It happens. Okay, so software should have caught this. So you've just got a little piece of copper floating around that's not really doing anything. I probably would have deleted that, or preferably my software would have caught that and deleted it. Same thing right here. I don't know what this little copper pore is doing other than causing potential trauma. Another crystal, not packed as tightly as the first one we saw. That thing was nuts. Okay, moving on. That was one half of the board. So we have what appears to be PoE coming from this mag jack out to, where was the connector? It comes out over here. Excuse me. So the mag jack connection comes to here. And then from there, we've got these 2 pins. We run it through more than likely a diode to prevent reverse current protection, or provide reverse current protection. And then we start with filter cap, a 0 ohm resistor. Sometimes you'll see engineers do that. It kind of acts like an inductor. It'll drop high frequency signals away. So Other times you'll do that is so you can break it for test. A capacitor bank. And then we go from there. So that just looks like a bunch of reservoir capacitors and then a well, not even a decoupling. Probably just a low inductance one. And then we drop into a tiny trace into this guy, which might be a power control IC. I don't know. But you can see where, again, they've tied with arrays of vias all over the place. The drill operators really love it when you do that. I mean, really love it. I highly recommend it. I'm kidding. They don't like it, but it's good practice. And unless you start packing them really, really tight, it doesn't really cost that much more. Here they tied something with 6 vias. I don't know what. So, Coilcraft. So this is an inductor. So it looks like this whole part of the board is power, filtering and distribution. So what it appears that happens is power comes in these pins, goes into these circuits, and then gets converted, buck, boost, depending on what voltages they decide they need for their stuff. And it all moves over here until it comes out of these headers here. And then it goes back into the other side of the board. And then once in the other side of the board, so these should be all controlled voltages, and then it starts running stuff. All right, then all of that stuff goes out into these tiny, tiny, tiny connectors, these tiny mating connectors. Crazy. Okay, so comes out of there. That's going to take me some time to fix. And goes into here. So let's figure out how this comes apart. We'll do it. We'll do it together. So the first thing I'm going to look for are screws, of which there are none. And then the next thing I'm going to look for are clips, like that one. And see if things move, and I don't think they do. So then the next thing we're going to do, we're going to have to get a little mark smash on this, I'm afraid. I hate doing that. No, I don't. I love doing that. Let's see, let's see. Just coming underneath the stickers here, see if I can see if they're load-bearing stickers. They are. So those stickers keep this metal thing on. Interesting, interesting. Okay, so all we did was remove some stickers. So they're gone now. I mean, that's important. I mean, if that's what I was trying to do, I did it. Okay, I was hoping that would be more effective. It did nothing. Oh well. And unless you've got experience taking each specific thing apart, that happens sometimes. Live and learn. All right, there are those mating? Yeah, those are mating pieces. Those aren't useful. So Keyence, how did you put this together? How? Let's get this piece off. Christian, do you see anything I could try, buddy? Before I go to Mark Smash? Let's see. Christian says, trust the process. Okay, there is some separation between these two pieces of plastic. I wonder if I can exploit that. And it could be that these things are welded together, in which case I really have no choice but to mark smash. But we're going to give it another second, look around, see if I can't figure anything out. Whoops. Okay, people. It's time. I've kept you waiting long enough. We're mark smashing. So right now I'm going for the corners, exploiting its weak points. And then we'll know after we get it open what the right way to do was. But I just don't see it right now. Those of you that are watching this online, feel free to yell at the screen. Leave a comment or two saying, "You Neanderthal, what are you doing?" Christian, I like your idea of the angle grinder. That would solve our problem in a hurry. Okay, quite obviously this thing's not going back together, so that's okay. We still have 8 of these channels left in the stack. There we go. Something happened there. Let's finish cutting that. So it was on the back side near the set switch. There was a clip. Okay. Die, case, die. Rawr. Mark smash. Okay, so we are seeing definitely an HDI board. Odd that I must have just moved that then. They're using little bits of copper to act as RF shielding, probably for regulatory compliance. Could be for heat dissipation. This, my friends, is a HDI board. Takes a really good engineer to design something like this. Double-sided. Oh, man. Gosh, Christian, what do you think an assembly like this must run? Proprietary connectors. I've never even seen these little clip-ins before. And there is no such thing as mark proofing. They can build stuff stronger all they want. I'll just go get me a bigger hammer. And when in doubt, C4. Okay, so back near this, near the back side, and on this side there was a clip that could come out, or, I mean, I don't know if it was ever supposed to come back apart, but it looks like it is possible to take these apart non-destructively. But I didn't know that before, and I didn't want to spend, 15 minutes examining it under a microscope to figure it out. We've got that teeny tiny LED display, and it actually looks, I'll show it to you in a second here. Looks like it's built onto a board. So here I think we're going to find LEDs under, I'm sure we're going to find LEDs under each one of these little holes. And then you might not be able to see it, but they soldered a board at right angles here. So I wouldn't be surprised if the LEDs are not even encapsulated, if they're just built right onto the thing. Let's see. Mark smashed unintentionally. Mark strong. Mark angry. Rawr. That's cool. Oh, we got to look at this first. You're going to like this. All right. Microscope is 5. They made a board, an HDI board, and they wire bonded the LED right on top of that thing. That, you don't see that often. That is cool. So each one of these is an LED. Usually when we see LEDs, they're in a case, right? They're encapsulated for soldering on. Well, what they did was they bonded these diodes straight to exposed LAN pads, and then all of these are little gold wires. I don't know if they're anodes or cathodes, to be honest with you. I can't see anything that clearly, but they just built a board. That is cool. How much does that cost? Man, this is why Keyence stuff is so expensive. All right, let's get that the rest of this plastic case off. So now that we have the outer case off, you can kind of see clips. There are ways to remove the rest of this, I hope. I don't want to damage that LED board. I want to see if I can get to it. What do we need to do? What do we need to do? So Christian, do you have, I mean, I don't know anything about prices. Do you have any idea what all of that would cost, buddy? I mean, I know you don't know for sure, but I mean, you got to imagine they made a full panel of these things. And this stuff is tiny, 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 tiny. All right, so we've got it apart. STM32F103 looks like it's running things. How many pins is that? That's a lot of pins. Big fat connectors, all gold plated. And these things all daisy chain. So just taking a look around, some of the things I like, some of the things I don't. Where you can, I always do like seeing multiple via arrays. Lowers inductance, higher current carrying capacity. If you lose a via, you don't lose the board. I mean, it's all upside if you can get away with it. But on a board this tight, I'm sure they couldn't get away with it often. This stuff is tiny. These components are ridiculously small. Looks like we've got a board that they didn't bother cleaning. That's never good. You always want to get this crap off because it can cause latent failures. You can have creepage occur. The schmutz can trap moisture, and then you end up with calf failures. It's conductive anodic filament. Vias all over the place. Again, I'd like to see slightly larger annular rings in case, you know, one of these vias tries to break out during the drill process. But man, this stuff is tight, and we haven't even looked at the other side yet. But again, more schmutz. That does not look like no clean flux to me. This looks like rosin core, which will lead to failures. It takes years, but it happens. They're latent defects. So clean, 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 clean whenever you can. All right, so this metal piece here, this is the LED emitter and receiver case. This is what this whole board is built to do. All of that to run an LED and a sensitive detector. But look at all that schmutz, man. No, Keysight, clean your boards. Talk to Mike Conrad. So we're just looking ever so slowly. Man, this is an HDI board. This, for those of you who have never laid out a board, this is, nightmare fuel. It takes a talented engineer to put this many things in such close proximity and, worry about signal integrity and return paths and all that other stuff on multiple layers, multiple boards. It follows a logical sequence. They moved all the power to one side one board, and then all the signals to the other, and separated them by quite a bit of distance. So anyways, is there anything else you want to see before we go? I know I ruined your lunch, Christian. Sorry. All right. Then I will share with you one last thing. We've made an improvement to mark voids of warranty, and I completely forgot to do it when the cat was screaming. But here it is. You're going to love this. We've got now the ability... DFA, Design for Assembly. Can we actually put your board together? Can you, sometimes people will put the parts too close together, or they'll have the wrong land pad patterns, and we just can't do it. But it's actually a little bit more complicated than just, can we do it, right? Because we can do a lot of things. You can also drive with your feet. It doesn't make it a good idea. See, the next thing you need to worry about is yield. And what's yield, Elijah?
Yield is going to be basically how many boards we're going to get, good boards we're going to get, because there is that factor of, some of those boards aren't going to be good when we make them. Some of them are going to be etched off a little bit on one hole. And again, one wrong hole or one bad trace and the board's no good. So it's something you have to take into consideration.
So what would a good yield be?
For us, we try to stick to 90 to 95% yield. We can usually do that. Basic designs, they're at 100 right now. We're doing really good. Haven't seen a simple mess up. We keep track of all that.
Now, the reason that I bring that up is when you design boards like this, you really do want to have a high yield, because if anything goes wrong, you're paying a lot to put this board together. To make an HDI board is expensive. To put this many parts on both sides is expensive. To have one of these fails is going to cost you a lot of money. So you want to do things that increase yield wherever you can. And the easiest ways to do that are, if you can, use a slightly bigger trace than a smaller one. Use a slightly bigger annular ring than your manufacturer requires. You don't have to do that on all of them, but if you do that on most of them, you're just decreasing the chance that something's going to go wrong. Use teardrops, right? See how this circle is longer and it kind of points in an arrow in one direction. That is so if this drill wanders down, if the hole's there, it's not going to break through the copper and it's not going to destroy the trace. Micro vias are expensive. If you can, you can't always, and I'm sure they couldn't on this board with as tight as everything is, but if you can do through hole vias, you're going to save yourself some money. And if you put this much energy into a board, this much work, by all means, make sure that it's washed. What it looks like to me is that this board was like half cleaned. It's weird. I can't explain it. Why all of this rosin or flux is floating around these pins in some spots and not others, I just couldn't tell you. I would have to ask my friend Sebastian, but Sebastian's not here. So that was fun. I don't know about you, but that was kind of a, oh, I'm not on screen, am I? There we go. I don't know about you guys, but that was kind of fun. That, which one am I on? I'm on over here. That was kind of fun. I really had fun taking apart the Keyence stuff. I got all of this, the controller and everything, at auction for like 15 bucks. It works, except I don't have the software or the PLD to run it. But still, though, I do plan on putting the control board back together. I'll just have to get the right headers and do it. And if I would have futzed around with that for a while longer, I could have gotten those off. It was concerning me that I was dumping that much heat in. Anyhow, if you enjoyed the stream, if you had any fun at all, please tell your friends, tell your neighbors, tell your friends' neighbors, tell your neighbors' friends. It could be a lot of fun. I really do hope that you guys join, subscribe, tell your friends to subscribe. And if you want to see these in a different format, we've been kicking around the idea of having them edited down. If that's something you'd like to see, please let us know in the comments below. If there's any ideas that you have that I could do to make this stream better, let me know. I'm doing it for you. I get to take stuff apart, so I guess that's for me. But I'm hopefully learning you something. I don't know. I do hope you learned something. With that, this has been Mark Voids a Warranty. I'm Mark. Definitely voided a warranty today. Love you, Keyence. I really do appreciate you joining me. If you ever have any assembly needs or manufacturing needs, please reach out to Advanced Assembly, aapcb.com. They're the ones that are paying me to do this. Thank you so much.